Hi everyone, today I'm going to present my final project, Influence of Sound Absorbing Material Distribution on the Room's Acoustic Response to Moving Objects. First, let's start with a simple room. Imagine a room, it could be a classroom or perhaps a bathroom, and think about singing in that room. Some of you may have experienced singing in the shower, and what did you hear? Yes, we hear the reverberation created by the reflections of sound of the wall. But what happens if we cover the walls with thick blanket? Yes, we notice the sound become drier. This is because the blankets absorb some of the sound in energy, reducing the reverberation time and changing the room acoustic environment. Now let's think a bit further. What if we only cover certain parts of the rooms with blanket and keep changing the position of this blanket each time we measure the room acoustic response? Would the acoustic environment change with each adjustment? And the answer is yes. A previous research has demonstrated that the spatial distribution of absorbing materials influences their absorption efficiency. In other words, the distribution of absorbing materials can impact the room's static acoustic environment. But now let's push the thought experiment a bit further. Suppose there is a moving object in the room, maybe a basketball or something smaller like a tennis ball. What effect would the movement of that ball have on the room's acoustic environment? And if we keep adjusting the blanket position while allowing the ball to move through the room at a consistent speed, direction, and distance, how would the room's acoustic response change? And this brings us to the central research question of my project: influence of sound absorbing material distribution on the room's acoustic response to moving objects. Next, let's talk about research purpose. As I mentioned earlier, one of the points my research focuses on is the distribution of sound-absorbing materials. So in this context, how do we define the distribution of absorbing materials? This brings us to the first research purpose, to define and quantify the spatial distribution of sound absorption. Now let's look at a previous study. In the research influence of sound-absorbing material placement on room acoustic parameters, they investigate how the position of sound-absorbing materials affect room acoustic parameters. One set of experiments shows that the absorption efficiency of materials varied depending on their location. As shown in the figure, as the absorbing panels will move toward the room corners, the absorption coefficient in the high frequency range decreased significantly compared to one placed at the center of the floor. Another experiment did demonstrate that moving the absorbing materials to the center of the ceiling gradually decreased the overall reverberation time, especially in the 500 Hz and 1000 to 2000 Hz range. The study concluded that in the reverberation chamber, the worst position for reducing reverberation time was in the room corners, followed by any junction between two walls. When placed at the center of the floor, the absorption coefficients were maximum, increasing by over 20% at all frequencies. So based on these findings, I propose a preliminary method for quantifying the surface absorption distribution using the weighted coefficient of variation method. We know that standard deviation is a good way to measure the degree of data dispersion. However, a limitation of standard deviation is that it uses the same units as the original data, making it harder to compare two datasets when their mean values are quite different. The WCV overcomes this issue by dividing the standard deviation by the mean, converting dispersion into a relative unitless measure. This way, WCV consistently represents relative dispersion, making it easier to compare data metrics regardless of their mean value. So let's look at a demonstration of applying WCV to quantify the uniformity of different distribution metrics. As shown in the figure, we have four surfaces, each divided into 25 areas with different absorption coefficients. Based on the findings from the earlier study, I defined a weighting matrix where the central region have the highest weights and the corners have the lowest. Calculating the WCV for these four surfaces, we can see that the most uniformly distributed surface, surface 1, has the lowest WCV, while surface 2 and 4 have higher WCVs. Surface 3 with the most varied distribution has the highest WCV. With the quantitative index for spatial distribution established, we can proceed to the second research purpose, to establish a framework for quantifying how different absorption distributions impact the sensitivity of room's acoustic response to moving objects. Now let's talk about my research methodology. To investigate my research question, conducting experiments is necessary. There are three experiment methods that we can choose, which is actual measurement, scale model experiments, and computer-based acoustic simulations. As the preliminary experiment, simulation method allows us to easier control variables, making it more suitable for the initial study compared to the other two methods. In the previous research, they compared the measured and simulated reverberation times and calculated the relative error between the two methods. The results indicated a high level of consistency. As shown in the figure, the simulated and measured values of the reverberation time exhibit a high correlation, indicating the high feasibility of the simulation method. In contrast, another study compared the experimental results from scale models with those obtained from software simulation. The findings showed that while both methods demonstrated high consistency in a low frequency range, the high frequency range shows different values due to the air attenuation, material absorption models, and audience absorption coefficients in the scale models. Additionally, in terms of modeling time and cost, computer simulation is more suitable for initial experiment. In summary, given the high degree of variable control, parameter definability, and strong correlation with actual measurement results, software simulations are selected as the preferred method for the initial acoustic experiments in this study. Therefore, I choose Audion to conduct acoustic simulation experiments. Audion is a platform designed for simulating indoor acoustic, employing a hybrid method that integrates three algorithms: the ray tracing method, the image source method, and the energy method. Now, regarding the experimental design, as shown in the figure, we have a room, and its surfaces are divided into several areas. For demonstration purpose, I have divided into 9 areas. Each area represents different absorption coefficients, and we can categorize this distribution into different experimental groups. Next, we place a moving object in the room, represented by the cube in the figure. In each experimental group, the cube will move in the same direction and the same speed and covering the same distance. During this movement, the room impulse responses will be measured at each time point. By collecting data across different experimental groups, we can obtain various acoustic parameters such as reverberation time, clarity index. Analyzing these parameters will allow us to examine the research questions. How does the distribution of sound-absorbing materials modulate the room's acoustic response to moving objects? Now let me talk about my work plan for the upcoming summer. The first step will be primarily dedicated to establishing the necessary experimental setup based on the design experimental framework. This will involve creating a detailed experimental checklist and systematically conducting the simulation to generate the required dataset. I plan to complete it within 6 weeks. Following this, I will focus on data processing, specifically developing a MATLAB script to analyze the collected data, extracting key acoustic parameters, and visualizing the result. This will take me 2 weeks. The objective here is to identify patterns and quantify the relationship between impulse responses variations and the spatial distribution of sound-absorbing materials. In the next step, the focus will shift to building a quantitative framework that establishes the correlation between the distribution of absorbing materials and sensitivity of room acoustic response to object movements. This model will provide the basis for further analysis and potential recommendation for optimizing room acoustic design under dynamic conditions. This will take me 3 weeks. And finally, it will take 2 weeks to complete the project report. But the progress of the report will also be updated in the previous stage. Thank you for listening. I'm happy to answer any question you may have.